So we're going to take a look at exponential functions today. And what these are, it's b to the x. Now, x is any real number. So that means x could be a whole number like 2, 3, 4, 5, 6. It could be 0. It could be a rational number like 1/2, 1/4, 3/4. It could, all those could be negative. It could be irrational. Now b, we're going to have b greater than 0 and also not equal to 1. And just to kind of discuss why this is true, for say suppose b was equal to 0, what would happen? Well, there's a few things. Let's say we have f of x equals 0 to the x. Well, what this will be equal to depends on what we choose for x. Now, if x is greater than 0, well, this just becomes 0, because you can take the square root of 0 is 0, 0 to the 4th is 0. That's perfectly fine. If x is equal to 0, though, you get 0 to the 0, 0, 0. That's undefined. You can't give 0 an exponent of 0. Can't do it. Finally, if x is less than 0, say x is like -2. So f of -2 would be 0 to -2, 1 over 0 squared, because you take the reciprocal with a negative, and that just gives you 1 over 0. And again, that's undefined. So if we let b be 0, we run into some problems. It's just 0 for x greater than 0, but it's undefined when x is 0 or x is less than 0. Really, an easier way, instead of using a function like this, you could just say this: f of x equals 0, and then just define x to be greater than 0. This does everything that this does. This is much easier. So that's what happens if we let b be 0. Now, what about 1? Why can't b be 1? And to be honest, there's really not a great reason why you couldn't let it be 1. F of x equals 1 to the x. The reason they really don't do much with this is that it's just equal to 1. That's it. It's just a flat line. And really, it might be just a little simpler just to say, just let f of x equal 1. And just don't even bother with that. So that's what happens if you let b, the base, be 1. But what about the base being negative, less than 0? Let's say we have this. F of x equals -4 to the x. Well, there aren't any problems for x equals 0. So for x equals 0, it's just going to be 1, because anything with a 0 exponent is 1. Where we got to be careful, though, and if x is going to be, say, well, hold on, if it's a whole number, so we have this. Let me organize this a little bit differently. This will be equal 1 for x equals 0. And we're not going to have any problems for like whole numbers. Like if x is squared, -4 squared will be +16. If x is -2, for example, say we had this. So f of 2, again, it's just -4 squared. or 16. And then f of negative 2, no problem here. This is 1 over negative 4 squared, or 1 over 16. So we're okay for x being 0. We could let x be 1. It's just going to negative 4 to the first power, which is negative 4. It could be 2 is fine. You get 16. Negative 2 is fine. You get 1 over 16. But where this becomes problematic for sure f to the 1/2. This means the square root. And let's say we're going to go with a positive square root here. If you go with the positive square root, what you're going to be getting here is the square root of negative 4. And since we're dealing with real numbers, and this is complex, we can't do this. In fact, we're going to run into this problem whenever we have an even root somehow coming out of our exponent. It could be a 4th root, 8th root, and it could be a combination like negative 4 to the 5/4. So something like this. If you had like f of 5/4. Or we'll stick with something familiar, 5/2. More familiar. And so you could rewrite this negative 4 to the 1/2 times 5. Which would be negative 4 to the 1/2. All of it raised to the 5th power. Or you'll end up getting, again, that square root of negative 4 raised to the 5th power. And regardless of what's happening with this 5th power, you're still stuck taking the square root of negative 4. And that's a problem. So the issue we're going to run into is that if we let b be less than 0, every time we get some kind of a rational exponent that has an even root, could be 5/2 or 5/4 or anything that has an even denominator. So like something like this, you'll run into just the same type of trouble if you had something like 3/8. Anytime you have an even root or an even denominator, it means you're taking an even root. Even root of negative numbers is going to mean complex numbers. And that's going to be an issue. Essentially what that means is our graph of f of x equals b to the x is going to be full of holes wherever these even denominator rational exponents occur. We just have a function that's punctured full of holes. So to avoid that, we're going to just have b be greater than 0 and not equal to 1. So now, something we want to look at is how to graph this. And there's sort of a trick. We're going to first break this up into 2 cases. Case 1. B greater than 1. Now again, we want b greater than 0 and not equal to 1. So we're going to look at b greater than 1 and then b when it's between 0 and 1. So for this case, what we're going to do, we'll do an XY chart. And let's say let's use an example. Let's say our f of x. We need to be greater than 1, so let's let b be 2. Let's go with 2 to the x. Now let's graph this. Now, a trick here is to use 3 particular points. And here, let me do this more vertical, because I'm going to need the space. Let's let x be negative 1, 0, and 1. So that means 2 to the x is 2 to the negative 1. And that means we take the reciprocal, 1 over 2 to the positive 1. Again, when you take that reciprocal, the negative goes away. You get 1 over 2. Now, 2 to the x, when x is 0, that's just going to be 1. And then 2 to the 1, because x is 1, well, that's just going to be 2. So these are the points we have. Negative 1, 1/2. 0, 1. And 1, 2. So now let's graph these. So negative 1 and 1/2 is here. 0 and 1 is here. And 1 and 2, let's see, is right about there. And so we connect these going left to right. Kind of a swoop. And then out here, we're going to keep dropping down, but we're never going to cross the x-axis. This x-axis is a horizontal asymptote. And what we're going to get in general for f of x, so this is going to be f of x equals 2 to the x. In general, what we're going to get is something like this. So for f of x equals b to the x, when b is greater than 1, we'll have negative 1, 1 over b. We're going to have 0 and 1. That's always going to be there, unless there's a transformation, which we'll talk about in a bit. And then 1 in b. And the general shape is going to be this. And then we have that horizontal asymptote. For b greater than 1. So that's the general shape of that graph. Now, I mentioned we're going to have two cases where b is greater than 1, and then we have the second case where b is between 0 and 1. So for that, let's say we do this. F of x equals 1/2 to the x. So we're going to do the same process. X 2 to the x, oh sorry, 1/2 x. And then we let x be negative 1, 0, and 1. So again, using these three same inputs, 1/2 to negative 1 means we take the reciprocal. That's 1 over 1/2 to the 1, which is just 1 over 1/2, and then 1 divided by 1/2 is 2. Now 1/2 to 0. Well, that's just equal to 1. anything with a 0 exponent other than 0, you're going to get 1. And then 1/2 to the 1, well, that's just itself, 1/2. So the 3 points that we get, -1, 2, 0, 1, 1, 1/2. So now let's graph this. So taking a look at this, we have -1 and 2. Again, we have 0 and 1. That's always going to be there, unless we do a transformation. We have 1/2. So if we connect these going left to right, it's going to swoop down like this. And then we have a horizontal asymptote that, again, we're not going to cross. And so this is f of x equals 1/2 to the x. So in general, when b is some fraction between, or maybe not a fraction, maybe it's some irrational number between 0 and 1, when it's any number, real number between 0 and 1, we're going to get this general form. Now remember, b in this case is less than 1. So that means if this is 1, b is going to be, say, down here. But then 1 over b is actually going to be way up here. Like, let's say b is 1/2. Well, 1 over b, or 1 over 1/2, well, that's 1 divided by 1/2, and that's 2. So 1 over b in this case is going to be way up here. And so the general shape is this. -1, 1 over b. Again, 0 and 1, and then 1 and b. It drops down like so. And there's that horizontal asymptote. And there we go. These are the general shapes of the graphs for f of x equals b to the x. Now, what we can do is, just like any of the canonical forms that we've seen, we can transform these. And the key thing to remember with transforming these, you're not just going to transform the curves, you're also going to move around the horizontal asymptote as well. So let's see. Let's say you have something like this. So 2 to the x plus 1. Well, what's going to happen here? Let's start out with our base function, 2 to the x. And what we're going to have, it's going to pass through 0 and 1. That's always going to happen. You have -1 and 1. And then we have a point of -1 and 1/2. Maybe 1/2 here. There's 0 and 1. And then we're going to have 1 and 2. So very roughly, this is our graph. And don't forget that horizontal asymptote. So this is going to be f of x equals 2 to the x. So what we do when we transform this, this means we're going to raise it up by 1. So that means all of our trace points here, they're going to be lifted up by 1. So -1.5 will be -1 and 1.5. Zero and 1 becomes 0 and 2. 1 and 2 will come up to 1 and 3. Now, we also need to raise the horizontal asymptote. That ran along the x-axis of y equals 0. It'll now run along y equals 1. And so this would be f of x equals 2 to the x plus 1. And there you go. The key thing with this is we want to make sure we're going to move the horizontal asymptote as well. All right, let's take a look at another one. Let's see here. So let's say we have this. Plus 2. So what we want to do here, we want to start out with our base function. So f of x is 1/3 to the x. And again, for test points, I recommend using x is -1, x is 0, and x is +1. And you can put these together real quick. So 1/3 -1, which is going to be 1 over 1/3 to the 1, which is 1 over 1/3, or 3. And then 1/3 to the 0 is 1. 1/3 to the 1 is just 1/3. And you'll kind of see a pattern with doing this. If you use these 3 inputs, when it's -1, this will become a 3. When it's 0, you've got a 1. When it's 1, it's just 1/3. And whether you use 1/4 or 1/5, you're going to see the same kind of pattern. So the points that we have, -1/3, 0 and 1, and then 1 and 1/3. So if we draw our base function, there's 1, 2, 3. So -1 and 3 is here. 0 to 1 is here. 1/3, so this is basically 1/3, 2/3, and a whole. So this would be about 1/3. And so this is our horizontal asymptote. So this is going to be f of x equals 1/3 to the x. So now we need to do the transformation, and we're going to do the horizontal transformation first, x minus 1. So what this means is we're going to take each of these points, we're going to shift it over 1 to the right. Remember, x minus 1 means we shift to the right, x plus means we shift to the left. Sort of counterintuitive, but that's what we do. And so what that means well, we had a point at -1 and 3, that moves over 1 to the right to 0 and 3. Then we had a point at 0 and 1, that moves to the right to 1 and 1. And then we had a point 1/3 and 1 was right about here. That's going to be 2 and 1/3. Actually, 1 and 1/3. Now it's 2 and 1/3. And then the horizontal asymptote, it's going to technically shift over, but it's just infinite here, so you don't see any difference. And so this becomes f of x is 1/3 to the x minus 1. So now what we need to do is deal finally with this plus 2. Now plus 2 means we're going to bring each of these points up 2 units. So this will go from 1 up to 3. This will go from 3 up to 5. This will go from 1/3 to 1 1/3 to 2 1/3. And then the horizontal asymptote, instead of y is 0, it's going to come up to y is 2. So we're adding 2 to everything. So what that's going to look like so we can move this asymptote. We'll go from the x-axis up to 2. And then the point located at 1 and 1, it's going to move up to 3 and 1. And the point that was 0 and 3, it's going to go up 2 to 0 and 5. And then the point that was at 1/3 will go up to 1/3, 2 1/3. So from 1/3 to 1 1/3, 2 1/3. Then we go through like this. And there you go. So that's how we can translate these things. We use the same approach as we did with the other functions we look at transformations for. The thing you want to remember is you're going to take this horizontal asymptote with you. All right. So something else that comes up here, there's a special kind of number that comes out of exponentials. And it's this one, E. It's approximately 2.71. I always forget this. Let me get a calculator to pull this one up. .828, and so on. Now, where this comes from, it comes from something that we call a limit. And the idea of a limit This is an idea you'll get in calculus. But basically what it says, as n becomes bigger and bigger and bigger, eventually this is going to settle on some number. So you could experiment with this. For example, if we let n equal 2, we'll get 1 plus 1 over 2 squared, which is 1½ squared, which is 3½ squared, which is 9/4, which is, let's see, 9/4, 4½, 2.25. So 2.25. Now let n equal 100, we get 1 plus 1 over 100 to the 100, which is 1 100th to the 100. Let's see what that turns out to be. Use my calculator. 1 plus 1 divided by 100 is that. And then give this an exponent of 100. It's approximately 2.070, and round it to 5. Now let's try n is 1,000. If you punch this into the calculator, you get approximately 2.71692. And finally, let's do n is 1,000,000. So approximately this will be 2.718280469, and it goes on and on. And at this point, when n is 1,000,000, we got our approximation for e. But this approximation gets better to this as n gets larger. So that's the idea of this limit. And the idea of using e as some special number, well, it comes up in mathematics, and let me show you how. So one thing that does occur is you have this idea of compound interest. And the idea of compound interest is this. You start with what we call simple interest. So you're charged an interest rate for when you, say, borrow money. It's like rent. When you borrow money, you've got that money, no one else can use it. Sort of like renting a house. It's your house or your apartment. Nobody else can use it. So you pay rent on that apartment. You're also going to kind of pay rent on this money. It's sort of one way of thinking about it. And we represent interest with some percent. So this will be the interest rate. And a responsible interest rate is going to be less than 100%, way less than 100%. We let P be the amount we borrow. We call this the principal. And what happens is we borrow this money for a period of time, say a year. And after 1 year, we're charged interest or rent on this. And so the total that we have to pay back, we call that A. It's the amount we borrowed plus the interest. So the way you compute interest is you multiply the interest rate to the principal. So we call the interest I. We'll say this is P times R. And so what we'll get is the total is P plus the interest, which is P times R. And we can factor out the P. So at the end of the year, this is what we're going to pay, what we borrowed plus the interest we owe on this, because we're renting this money, so to speak. And then as sort of a trick of math, we can pull out the P, and that just looks kind of cool. But let's say we borrow this money for more than a year. Well, what we'll end up doing is our interest is going to start to compound. And what this means is that we're going to be charged interest not just on what we borrowed, but also the interest we owe. Like, let's say we don't pay it. Well, what the person can do, who we're borrowing the money from, could put this interest back into our debt. They'll say, well, you not only owe me for what you borrowed, but you owe me for the rent on what you borrowed. So now our principal for the next coming year, well, it becomes this. Everything we owed from the previous year. So now the second year goes by. And what happens is what we owe is the principal plus the principal times the interest. So again, that's our principal. And so this is what we owe at the end of the second year. Now we can clean this up a bit. We could factor this out. Say this is A equals P1 plus R times 1 plus P1 plus R times R. You can always multiply by 1. Factor P times 1 plus R, factor out P times 1 plus R. And so now at the end of the second year, we get this. And so we'll leave this 1 behind, and we'll leave this R behind. Now look at this, it's just 1 plus R. So we'll get this 1 plus R squared. And then we say, well, we're still not going to pay the interest, and we're going to keep this going for a third year. And as you could guess, at the end of the third year, this is how much we'll owe. End of the fourth year. And so on. So if we do this for T years, from when we started, so say it's been T years total, what we'll owe is P 1 plus R to the T. All right. So this is after 2 years, after 3 years, after 4 years, after some T years into the future. So now what happens with compound interest? It's a little more complicated than this. The way compounding works is you're charged interest throughout the year. And what you're charged each time is a fraction of the original interest rate. So let's say you're charged twice a year. So at each time, say at 6 months and then at 12 months, you're going to be charged a rate of R divided by 2. So that means our formula becomes P 1 plus r divided by 2. And what happens here is we're being charged interest twice in this 1 year. Now, when we have t here, t is the number of years that we were being charged. And this is the interest rate. Again, this is just the interest rate for each time we're charged. This is the interest rate each time we're charged t times. So what t basically represents is not just years, but this exponent represents the number of times we're charged, period. Now, since we were charged at the end of each year, the number of times we're charged is equal to the number of years in this case. But let's say we're talking about 1 year. How many times are we charged in this 1 year? Well, we're charged 2 times. And so we typically write this as the number of times per year times the number of years. So, for example, again, let's say we didn't do this for 1 year. Let's say we did it for 4 years. So that means twice a year for 4 years, we're going to be charged interest. Now, since we're charged twice a year, the interest rate is still r over 2. But then the total number of times we're charged is twice a year times 4 years. And so what we get is the compound interest formula. Let's say we're charged or compounded in times for interest. So for your notes, let me just put this in. The total charges. So this would be the total number of charges for 1 year. And this is if you're being charged twice a year. So if you're being charged twice a year, this is your interest rate, and the total number of charges for 1 year is 2 times 1. Here are the total charges for 4 years. And again, because it's twice a year for 4 years, you're going to get 8. So in general, the total number of times you're charged, it's the number of times per year times the number of years. In this case, it was 1 year. Number of times per year times the number of years. Here it was 4 years. So in general, we do this. So if we let n equal the number of times we're charged per year, the interest rate that we're charged is always r divided by n. And then the number of times we're charged this interest rate is the number of times per year times years. So what does this have to do with E? Well, one of the questions we might be interested in is this. What happens if we charge interest over and over and over again, more frequently than, say, twice a year? That's what we call semi-annually. Maybe 4 times a year, or we charge it quarterly. Maybe we charge it 12 times a year or monthly. Maybe 52 times a year or weekly. Or maybe 365, or if you're using the ordinary method, 360 times a year. In other words, daily. What if you charged interest continually? You were always charging interest, but you're always charging by this smaller interest rate as the number of times you charge per year gets bigger, bigger, bigger. So now we do that limit. what happens if the number of times that we charge the interest just increases infinitely? Well, what we're going to do a little bit of rewriting here. With the limit as n goes to infinity, we're going to rewrite this as 1 over n over r, like so. Because if you take 1 divided by a fraction, that just flips that fraction back over. Sort of a trick, like say 1 divided by 2/3 is 3 over 2. Now we're going to do a little trick here. We're going to let h, just going to pull h, just use it. Come up with h and let h equal n over r. And if we do that, we're going to make the observation that this means we can multiply both sides by r. N equals h times r. And again, you can get that by multiplying both sides by r. You'll get cancellation of r over here, get r times h over here. So let's rewrite this. Now here's the other thing I want to make an observation of before I do any rewriting. As n goes to infinity, it gets bigger and bigger. What's happening to h? Well, if n gets bigger and bigger, even though it's divided by r, r is a constant. It's like maybe 0.05 could be r. But as n gets monstrously big, dividing by 0.05, that just makes things even bigger. Like if n is 1, then r is 0.05. So we'll let r be 0.05. So if n is 1, well, 1 divided by 0.05, this means h is 20. If n is equal to 10, remember, n's going to infinity. It's getting bigger and bigger. Well, h is 10 divided by 0.05. H is also getting bigger. It's 200. Let n be 1,000. You see where this is going. Well, 1,000 divided by 0.05 is 20,000. So as n gets bigger, h gets bigger. So this is what we're going to say. As n goes to infinity, as n just keeps getting bigger, bigger, and bigger, then h gets bigger and bigger. H goes to infinity. So now we're going to rewrite that limit. So we can replace this with this. So now we've got the limit as h goes to infinity. We had 1 plus, now h was equal to n over r. That's what we had here. And then n equals hr. So we had nt. Oh, and let me don't forget the p here. So now we have this, with t we have, well, now n is hr, and then we still have that t still there. But we replaced n with hr. So what we're going to do, there's a rule with limits that lets us basically bring the limit inside this multiplication with p. But we could kind of rewrite this a little differently. We could say, and this is going to help, this is p times 1 plus 1 over h. We're going to factor out r and t. So this is going to be h to the rt. And with the limit, as h gets bigger and bigger, this thing is going to become e. Remember, it's when this, we have 1 plus 1 over, we had n to the n power. Well, h is going to do the same thing that n does. It's just going to get bigger and bigger. So having 1 plus 1 over h to the h power is going to be the same thing. And as h gets bigger and bigger, we know what this is going to become. It's going to become e. So we're going to get to the RT, or PE to the RT. And you might have seen this formula before, but what this is, it's the formula for compounding interest continuously. And so what it is A equals P E to the RT. So E, it comes up naturally as we increase the number of times we charge interest in a year. And so that's sort of where it sort of comes about. And it comes up in other places too in mathematics. It's a very common number, actually. What pi is to geometry and trigonometry, you'll see E showing up in all kinds of places. So it's something that's you're going to be encountering it quite a bit in the future. All right. So just an example working with compound interest. Do a couple of these. You're going to have two formulas, the compound interest formula and the compounded continually interest formula. So typically what you'll get is something like this. So let's say you invest $1,000 at 7% interest, compounded, let's say monthly. How much money do you have after 5 years? So we're going to invest. It's not always about debt. Sometimes it's about investing money and doing what they call having your money work for you. So we're going to invest this money. Someone's going to borrow the money from us and we're going to charge them some rent, so to speak. And we're going to let them use $1,000. We're going to get 7% interest, hopefully. It's going to be compounded monthly. So that means they're going to be charged interest once every month. And the rate they're going to be charged is going to be 7 over 12. Oh, I'm sorry, 0.07. We need to convert this to a decimal always. When we do interest problems, we always need to convert the percent to a decimal. The way you do that, always divide the percent by 100, and that'll turn it into your decimal. So they'll be charged this amount of interest once every month. And so now we need to find out how many times we charge them over 10 years. Well, we're charging them monthly, so that's 12 times a year for 10 years. So that means 12 times 10 years is 120. So we're going to charge them this amount of interest, 0.07 divided by 12. I think that's approximately something really small. This is, so to convert a decimal to a percent, you multiply by 100. That moves your decimal here. So about 0.5%. We're charging over just over 0.5% per month. And we're doing it 12 times a year for 10 years. So the way we figure this out, though, we're going to just use our formula. It just makes life easier. So A is P1 plus R over N to the NT. Again, this is the interest we're charging each time. This is the total number of charges, period. So we plug everything in. And then again, there's that interest rate. And then it's 12 times 10. Now with this, especially when you get to this, use as many decimal places as you can. Here, let me get a slightly calculator that's sort of lost in a peculiar mode. So I'm going to have to use this one and figure out that mode later. But hang on to your decimal places until the very end. So this will be 1,000 times 1 plus, and then 0.07 divided by 12. And it's going to be, I'm going to give as many decimal places as my calculator will give. 5 threes. And this is to the 120. It's 120 right there. Add the 1 in the decimal. An exponent of 120. And again, we're going to use as many decimals places as we get on our calculator. Finally, multiply by 1,000. We're going to get 2,000. Rounding to the hundreds place, $2,000, $2,009.66. So what this says is this: if you invest in this account, put in $1,000, and if it's compounded monthly at 7% interest, so they actually charge 7 divided by 12, or 0.07 divided by 12, then, or 7% divided by 12. After 10 years, this is what you're going to have. Now, I think I might have said 5 years earlier. Let's say it was 10. Forget about the 5 years. Let's say it was 10 years. So after 10 years, this is what you're going to have in your account. So 10 years, they're going to double your money. So maybe that's not a bad deal. Now, another question, though, they could ask it like this. And again, I don't remember. If I said it was 5 years, forget that. Let's go with 10 years instead. Sorry about that. Now let's say we do something different. Let's suppose we have compounding continuously. Compounding continuously. Well, now we use that different formula. A equals P E to the RT. So we're still going to do this for 10 years. We're still using the 7% interest rate. We're still investing $1,000. So this means we get 1,000 times E to the 0.07 times 10 years, or 1,000 E to the 0.7. So you got to get a calculator out, figure this out, and again, use as many decimal places as you can. Let's see. So different calculator, look for a different location for E. A place to look for E, look for the LN button. And you usually have to, so far I've been hitting shift or second and then my LN button. All right. So again, so what we're going to get is 72.51. Let me double check my math real quick there. Oh, made a mistake. Sorry about that. I miswrote that. Seemed a little funny. Pardon me for just a moment. Gosh, I must have typed in something peculiar. It's this. All right, so this is the number, e to the 0.7. I don't know what I typed in before. Let me see if I can figure that out. 0.07? That might have been, I might have accidentally typed in 0.07, but I multiply by 10 to get 0.7. E to the 0.7 gives you that. All right, so when you multiply by 1,000, we'll get $2,013.75. So it's a little bit more. If we compound infinitely, basically, it's only a little bit more because we had about $2,009 and I think 60-some cents. For compounding monthly, if you compound infinitely, you only go up about probably $4, a little over $4. Well, anyway, well, those are exponential functions. If any question, let me know.